Supplemental math videos from Circle Christian School.
Circles and parabolas. It's too bad that poor Hypatia had to suffer such a tragic death. Who knows what she may have been able to accomplish? Some records attribute the hydroscopium to Hypatia. It was a clock fashioned of water-driven gears, most likely from a hydrometer.
All of the conic sections can be described or defined in terms of distance. For the ellipse, we can understand the distance definition with a little experiment. Suppose we drive two nails into the board like this, and we drape a string between the nails. Then we take a pencil and we stretch the string and draw the figure. Now the figure will be an ellipse. Now the string stretching sort of gives us an idea of the notion of distance here. If we take a point on the elliptical curve and we add the distance to those two nail points, add this distance and this distance, then we get a total. Now that total is the same for any point on the ellipse. That is, the total of these two distances would be the same as the previous total. And that would be the same for any point on the ellipse. And it only makes sense because the total of those two distances would be simply the length of the string that we started with to draw the figure. Well, let's talk about some terminology. The two points that were designated as the nails are called focus points, and the plural of focus is foci. If we identify a point right in between the two focus points, we're identifying the center of the ellipse. Now, a segment that goes through the ellipse and actually connects from one end to the other, but containing the center and the two foci is a major axis. At the end of the major axis, there are 2 points called vertex points or vertices. The segment going through the center, perpendicular to the major axis, is the minor axis. So here's the length of the minor axis, here's the length of the major axis. Now, if the ellipse is elongated vertically, like this, then the major axis will be vertical and the minor axis horizontal. Let's review the terminology. We have a center point, we have these 2 points as focus points, and these 2 points vertex points. Now let's talk about building an equation that gives rise to this ellipse. First, let's assume that the ellipse is situated so that the center of the ellipse is at the origin of the coordinate system. Now, it may make some sense that any equation describing the shape of this ellipse will need to give us information about the distance from the center of the ellipse to the end of the major axis, and also information about the distance from the center of the ellipse to the end of the minor axis. Well, if we call these distances A and B, then the equation describing this ellipse is this equation. Notice a plus sign appears between the 2 fractions and a 1 appears on the right side of the equation. And another interesting thing to realize is that A and X are both horizontal distances on the graph, and A and X appear in the same fraction of the equation. In a similar way, B and Y are vertical distances, and B and Y appear in the same fraction. When the ellipse is elongated vertically, the equation looks like this. Notice that the b squared and a squared appear to simply be swapped in this other equation. And that kind of makes sense when we think about the distances involved. Now we know that a is the distance from the center to the end of the major axis, and b is the distance from the center to the end of the minor axis. Well, a and y are vertical distances here, and a and y appear in the same fraction. In a similar way, b and x are horizontal distances, and b and x appear in the same fraction. Well, let's suppose we would like to identify the positions for our foci. It's pretty easy for us to do if we just call the distance from the center to the focus points a distance of c. Then there's a relationship between a, b, and c. And this equation gives us that relationship. Now, we can change this equation in a way to make it a little easier to remember. If we add c squared on both sides and subtract b squared on both sides, then the arrangement or the equation looks like this. And I think this is a little easier to recall because it's very similar to the Pythagorean relationship which we have some knowledge of, except the existence of the minus sign here, whereas in the Pythagorean relationship that would be a plus sign. But it's so similar that it's very easy to remember.
To construct the graph of the ellipse associated with this equation, we first begin by noticing that the larger denominator is under y, and that just tells us that we're going to be elongated vertically. Now, to identify a and b, we want the numbers that are squared to give these denominators. So the a value is effectively the square root of 25, 5, and the square root of 16 would give us b. So b then is 4. So now we have, let's see, if a is 5 from our origin, from the center of our ellipse, we go a distance vertically now of 5 in both directions. The b distance is 4, so from the center we go left and right a distance of 4. And we can draw the ellipse. Now, if we'd like the positions for the foci, we can make that calculation using this ABC relationship we talked about. We know c squared is a squared minus b squared. The a value we found to be 5 and b 4. So 5 squared, 25, 4 squared, 16. The difference is 9. If c squared is 9, then c is plus or minus the square root of 9. We want the principal square root, or 3. So that distance is 3, and it's along our major axis, so we go up 1, 2, 3, and down 1, 2, 3 to identify the foci. Here's another one now. This one is in a more general form, and we might think, well, gee, how do we begin the problem? Well, the prevailing characteristic about the equation for the ellipse that we look at is the notion that 1 is isolated on the right side of the equation, and that's how we want to attack the problem from the beginning. So we want to create a 1 right here. To do that, we'll divide through by whatever number this is, if it's not 1. So we'll divide through by 70. So we take this term, divide by 70, this term, divide by 70, and over here, divide by 70. Now we've got the 1 that we're after. Now look at what we have over here. Well, we have a couple of denominators. We notice that the first one is larger than that one, so we know that the a value is the square root of 14. And also we see that it's under x, so we're going to be elongated horizontally. And that's the important thing about the graph here that we need to notice. We want the number which is squared to give 14, so it's the square root of 14. So we might write this as the square root of 14 squared, and here the square root of 10 squared, in order to identify the values for a and b. A is the square root of 14, or approximately 3.7. B is the square root of 10, or approximately 3.2. Now we can pretty easily sketch the graph. Let's go do that. Now we know that we're elongated horizontally, so from the center, let's see, we go a distance of 3.7 to the right and left. .7 left and right. The b distance is 3.2, so we go up and down 3.2. And now we draw the ellipse. Now from the position of these points, the ends of the major axis, the ends of the minor axis, we can see that it's almost circular, isn't it? And that's an interesting topic, I think, for us to talk about. It turns out that when A and B are very much different from one another, we have a highly elongated kind of ellipse. When A and B approach the same size, that is the horizontal distance from the center and the vertical distance from the center for the minor axis become close to one another, we have a more circular kind of configuration. And indeed, if A and B are equal to one another, we have a circle. And we can even see it algebraically. Come back over here just for a second. If we had the same number here as here, let's say it's 20, just for conversation purposes, then we could multiply through by that value, by 20, and we would have x squared plus y squared equals 20. You see, and that's the form of a circle whose center is at the origin. So So it's important that we realize, I think, that the ellipse is a cousin, I guess, of the circle. Well, we want to put this one onto the graphing calculator now and take a look at what that looks like. Now, we know that we can't graph this directly because the graphing calculator graphs functions, and this graph fails a vertical line test, so it's not the graph of a function. But we can construct its graph by separating the original equation into two separate equations. One of the equations will be the top of the ellipse and the other will be the bottom of the ellipse, and you may remember this from studying the circle. The same technique is involved. Now, the way we will structure our equations for graphing, though, is to take the original equation and solve for y. And to do that, I'm subtracting 5x squared on both sides and then dividing through by 7 and then cleaning up a little bit. I want to write a distinct coefficient for x squared, and I'm writing it as negative 5/7 x squared. And then if y squared is equal to this expression, y is plus or minus the square root of that expression. And those two give us the expressions that we're going to graph. That is, y is plus the square root of this expression, and y is minus the square root of that expression for our two equations. Let's have a look.
The first equation has already been entered, and I'd like to show you something about the layout of the equation. This negative 5/7 x squared, now as it appears here, it looks like the x squared is in the denominator with the 7, and it's very important to enter these functions correctly in order to prevent that from happening. Now, this particular calculator has as its default the notion that the negative 5/7 is the coefficient of x squared. So we're okay with this calculator. But with earlier calculators, and with most calculators, you would need to do this. You would actually need to emphasize that negative 5/7 is the distinct coefficient of x squared. And so you would want to insert, and that's second, and then the insert button, open a parenthesis here, slide over a little bit, and then second and insert a closing parenthesis to show that distinct coefficient of x squared. But as I say, it isn't necessary on this particular calculator, and yet it is on some. Well, window settings, let's see. I'm setting up a square perspective so that we can see our conic section in an anatomically correct way, and with conics we'll want to do this, I think, in all cases. But I set an x minimum of negative 5, x max of 5, and then I calculated the y minimum and maximum for a square perspective to be these values. And I'm pretty safe here with the y minimum and maximum, you know, because the b distance turned out to be 3.2, and I'm a little over 3.3 here for these distances from the origin. So let's take a look at the graph. Now remember, this is only the top portion of the graph, and we look somewhat elliptical here, so it looks pretty safe. Let's enter the bottom part. There are actually two ways that I want to show you to enter the bottom part. We could enter the negative of what we see as y1, or we could enter negative y1, and we do that by pressing the vars button, and then we want y variables, so we'll cursor to the right one, and now we want a function, and we want y1, so I'm just pressing enter here, and now we have the negative of y1, so we don't have to go through and enter all of those various characters. But here's the bottom of our graph showing up, and sure enough it looks as we pretty much expected. Incidentally, notice the gap over here on the left side of the graph and the right side of the graph. We've seen that situation before when we were dealing with circles, and the reason for it is that we didn't set up friendly values when we set up our viewing window.
Let's construct the graph of the ellipse given this information. We have vertices at plus or minus 5, 0, foci at plus or minus 2, 0. We might start by structuring a little graph. Now, plus or minus 5, 0. 5, 0, negative 5, 0. Now, if these are vertices, we know that we have an elongation horizontally, and that tells us something about the structure of the equation. Foci at plus or minus 2, 0. These 2 points are the focus points. Now we also know that we have a center at the origin of the coordinate plane because the center is right in between vertex points. So away we go with the evaluation of the equation. Well, we know this much about the equation. We know it's x squared over something, y squared over something else. We know that we have a horizontal elongation so that we know the a value is under x squared and the b value is under y squared. We actually have that a value. We have, well, let's come back over here and make sure we understand that we have it. It's the distance from the center to the focus points, and that distance then is this distance. So A then is 5. And we also have the distance from the center to focus points. And that distance is C, and it turns out to be 2. Now we're still looking for B, but we know this much. We know that in our equation we have x squared over 5 squared, and then plus y squared over some unknown quantity equals 1. All right, let's find the B value. We would use that relationship C squared equals a squared minus b squared. We have information about a and c in this problem, so let's see, we have 2 squared equals 5 squared minus b squared. And I'm going to kick b to this side. B squared then is 25 minus 4. So b squared is 21. Now I could find b. B is the square root of 21. But you know what? I don't need the value for b. I really need the value for b squared because of the nature of the equation. If I wanted to construct the graph then and complete it, then I would need an approximation for the square root of 21 for that purpose. But I really just need b squared in order to plug in here. So I would put the b squared in as 21, and I'd probably rewrite this as x squared over 25 plus y squared over 21 equals 1. When the center of the ellipse moves away from the origin, we simply introduce the h and k that we discussed earlier when we were talking about the parabola. That is, we start with the idea that if the center is at the origin, then this is the nature of our equation. When the center is not at the origin, you see, we introduce h and k, h associated with x and k associated with y. So now we have binomials squared in these numerators. But the analysis is really relatively simple. When we see an equation in this form, we understand the meaning of all of the different parts. The a and the b haven't changed meaning at all, and we simply have the extra little nuance of the h and the k. Here's an example. We have in this equation, now notice a binomial squared in numerator in the two numerators, and therefore we know that the center of the ellipse is not at the origin. Let's identify some aspects of the graph. The center is at, well, let's see, h and k, and they follow minus signs. So the number following a minus sign associated with the x is the h. So h is 1, k is 5. So we have a center at 1, 5. Now let's come over here and identify that position. 1, 2, 3, 4, 5. All right, there's the center. Now, what about A and B? Well, let's see, which is larger? Oh, 25 is larger. So the A is found in 25, and it's the number squared to give 25, so it's easy to see that that number is 5. So A is 5, and for B, B is found as the number squared to give 9, and it's easy to see that that's 3. So let's see, an A distance of 5 means from the center, we go a distance of 5 in 2 directions. Now let's see, do we go left, right, or up and down? Well, the a squared is in this denominator, so the a is found here, and it's under y, and therefore we're elongated vertically. So from the center, we go up 1, 2, 3, 4, 5, and then down 1, 2, 3, 4, 5 to locate vertex points. And then the ends of the minor axis are a distance of 3 from the center. So from here we go 1, 2, 3, and 1, 2, 3. Now we can actually draw the ellipse if we'd like to do that. I think we'd like to write the coordinates of these important points as we go. We'd also like to identify the value of C so that we can locate foci. Well, let's see, we have the center. Now vertices we can read right off of the graph, and I can either calculate C now or or not. It's pretty easy to see those vertices. The one vertex is way up here. It's 1 and then up 10. So one vertex point has coordinates 1, 10, and the other has coordinates 1, 0. Now, let's notice something about the coordinates of the vertex points. They're taken from, or they can be calculated from, the coordinates of the center. You see, we were at the center, and then we moved a distance vertically in 2 directions corresponding with A. So really, it's as though we could make the calculation like this. It is, take the center idea, it's 1 and then 5, and I'm using the vertical component, the y value, and I add and subtract that A value. You see, I kind of want to emphasize that because sometimes the algebraic calculation is necessary. So you add 5 and you get this, and you subtract 5, you get that. Okay, so that's the idea. Now for foci, it's a very similar kind of thing because we're working off of the center and we go a distance of c in those 2 directions. And let's now make the calculation for c. I haven't done that yet. Let's come back over here to do that. We know that c squared is a squared minus b squared. So let's see, I have c squared then is 5 squared minus 3 squared. C squared is 25 minus 9. C squared is 16, so C is plus or minus the square root of 16. And we want the positive or principal square root, so it turns out to be 4. So C is 4. And from here, graphically, we go up 4 and down 4. And for the coordinates of the foci, it's a similar idea to this idea. We're working off the center, and we add and subtract with the vertical component. So it's the idea of making the calculation as 1 and then 5 plus or minus c. You see, that's the idea. So we're adding and subtracting 4, really, to this point in the vertical way. All right, so let's see. We have 1, 9, and then 1, 1 for 5 minus 4, you see, for that component. Okay, so that's the idea. Now, I want you to notice in the graph that the foci lie pretty close to the vertices. And it'll turn out that the closer these lie to the vertices, the more elongation that we get in the ellipse. And as these focus points move near to the center, we get a more rounded configuration. And we talked about the nature of the roundness of ellipses before, but only in terms of A and B. But really, the roundness of an ellipse is actually a measurable kind of thing. And it's based upon the notion of the relative size of A and C more than it is the relative size of A and B. Okay, and there's a name for the relative roundness of ellipses, and it's called eccentricity. And eccentricity is calculated by using this ratio. The eccentricity is C over A. Now, C is the distance to the focus points, you remember, and A is the distance to vertices. So in our problem, it's 4/5. Now, notice that the 2 values are relatively close to one another, and we have a fraction that's nearing 1. And the closer that the C value would get to A, the closer to 1 that we would get. And so we would have a more stark elongation under that circumstance. On the other hand, as C becomes smaller and smaller, you see, this fraction then would become smaller and smaller, approaching 0, and the elongation would be less and less, and the roundness would be greater and greater. So it's the idea that as E approaches 1, the ellipse tends to elongate, and as E approaches 0, the ellipse tends to approach the shape of a circle. This is the general form of the equation of an ellipse. And I kind of know, even just looking at this rather complicated looking equation, that it is the equation corresponding with an ellipse because I see both an x squared term and a y squared term. I see that there's a plus sign between those two second degree terms, and I see that these coefficients are different. If the coefficients were identical, it would turn out that this would be the equation corresponding with a circle. Okay, so let's put this equation into the standard form and discover some aspects of the graph. Well, to begin the process, we associate the terms involving x and the terms involving y with one another. So we'll rewrite like this. Now I'm bringing the minus 32x to this position. And now I'm going to leave a space right here for emphasis and write this term and then the 50y. And I'm going to take the existing constant term and kick it to the other side. And I think you see what's coming here. We're going to end up completing the square a couple of times here because the standard form for the equation of an ellipse is where we have some x value squared or some binomial involving x squared involved in the problem. So let's create that situation by completing the square. Now as we look at this, we have coefficients other than 1 for the x squared and for the y squared. So we need to force the factorization of these coefficients from the two terms involving x and y. You see, we're kind of thinking of the problem like this. See, that's the way we're thinking about it. So we kind of have a separate problem here and here within our overall problem. Well, taking the 16 out of these two terms, we get, let's see, 16 times x squared minus 2x. You see, and then here we'll pull the 25 out of those two terms, so we'll have y squared plus 2y. Okay, and away we go with completing the square. Now, completing the square here in parentheses, half of the negative 2 is negative 1 squared is 1. So we're going to add 1 in here. But if we add 1 in here, what are we really adding to this side of the equation? You see, what are we really adding? We're really adding 16 times 1. We're adding 16 over here. So if we're adding 16 on the left side of the equation, we have to add 16 on the right side. And back over here, let's complete the square here. Half of 2 is 1, 1 squared is 1, so we add 1 in parentheses. But what we're really adding to this side of the equation is 25 times 1, or 25. So we need to add 25 on the other side. Now let's clean up a little bit. We need to go through and perform the factorization here. So we have 16 times. Now factoring, we get x minus 1 squared. And then here we have 25 times y plus 1 all squared. And on the right, when we collect, we get 25. Now, is this the form we're looking for? No, because the form we're looking for has a 1 isolated on the right side. So the next thing we want to do is divide through by 25. In the interest of time and space, I'm going to show that step like this. We're going to take the right side and divide by 25. We're going to take this term and divide by 25. We're going to take this term and divide by 25. Now, we're looking for cancellation opportunities. Gee, I don't see one right here. I see one here, though. Let me just write this down. We'll come back and deal with this situation in a minute. The 25s go out here, and I have y plus 1 squared for this term. But for emphasis, I'm going to write this as y plus 1 squared over 1. And on the right, I have the 1 as expected. Now let's deal with this situation. When we have equations like this in standard form, the coefficient of the binomial squared is 1. And I'd like to create that situation here. And it's not too hard to do. It turns out that all we need to do is multiply that 16 by something that will cause it to be 1. And that something is its reciprocal. So we're going to multiply in the numerator by 1/16. But if we do that, we need to multiply in the denominator by 1/16 because we don't want to change the value of the situation. So really we're doing this. You see, 1/16 times 16, 1. And then 1/16 times 25 gives us a fraction in this denominator. A situation we haven't seen in the past, but not one that's too difficult to deal with. All right, so we have this, and then 1/16 of 25 is 25/16. All right, now we can identify the A and B. Now, where are the A and B found? Well, which of these two numbers is larger? 25/16 is certainly larger than 1. So the a is found in here. A then is the square root of that, so it would be 5/4. B is the square root of 1, so B would be 1. And now let's see, what about C? Let's go ahead and calculate C here. And you notice we haven't even gone to the graph form yet. And maybe we'll just avoid that altogether on this problem and work the whole thing algebraically. But if we have A is 5/4 and B is 1, we calculate C like this. All right, A is 5/4, B is 1, and our relationship between A, B, and C, we substitute for A and B and then evaluate for C. Now 5/4 squared is 25/16 minus 1 squared is 1, and 1 is simply 16/16. So 25/16 minus 16/16 is 9/16. C is the square root of 9/16 or 3/4. So C is 3/4. Now let's go through and identify the important positions, the important points involved in the graph. First important point would be the center. Well, the center is at H and K. H and K follow minus signs, and the center then is at 1, -1. So 1, -1, and that's how we would begin the process of listing all of these important points. Let's go through and do that. The center is at 1, -1. Now, vertices are calculated off of the center point. Now, we recognized that that first denominator, the denominator of the term involving x, was the one containing a. So we know we're elongated horizontally. And that tells us that we're going to take the coordinates of the center, and we're going to elongate, you see, to elongate horizontally, we're talking about horizontal distances from that point. So we're going to take the x coordinate and add and subtract that a value, you see, to get the coordinates for the vertices. So it's 1 plus or minus the 5/4, and when we make the calculation, 1 plus 5/4 is 2 1/4, 1 minus 5/4 is -1/4. And then the y component stays the same in both cases. For the foci, for the coordinates of the foci, we do pretty much the same thing. That is, we're operating off of that center. We take the coordinates of the center and think about adding or subtracting c to the x component for those coordinates. So it's 1 plus or minus c, and c is 3/4, so 1 plus 3/4 is 1 1/4, 1 minus 3/4 is 1/4. So these are the coordinates then of the foci. And we've made all of these calculations without even constructing the graph. So we can do an awful lot with these problems without even consulting with the graph or using it for reference. Consider this problem. Here we have information about a graph, and we'd like to write the equation associated with this information. We would start by sketching a graph, or starting the sketch of a graph using the information we have. Now, the coordinates of the foci allow us to think sort of this way. Now, let's see. We have one focus point at 0, 0, another at 0, 8. Here's the point 0, 8. And if these are focus points, then, gee, we understand that the ellipse tends to wrap around those, and so the ellipse is going to be elongated vertically. We also know that the center is right in between focus points. It's right in between our vertices as well, but we can identify the center right now. The point right between these two is the point 0, 4. Well, gee, with the information about the center, and the center is not at the origin, we kind of know the structure of our equation, don't we? We can kind of start to put it together. It is, let's see, we have a binomial involving x and h, x minus h squared, over an a or a b. Since we're elongated vertically, we know the a is under the y and b is under the x. So we have b squared here, and then we have y minus k squared over a squared equals 1. Okay, now what do we know? We know h and k. Well, let's put that in. We have x minus, now the coordinates of the center were 0, 4. So the h value is 0, and the k value is 4. Now I'm leaving vacancies for a and b. Let's start to talk about those. Now if this is our center, then this distance is c. So c is 4. All right. Now C is 4. Now let's use the other information. We have a major axis length 16. We know the major axis is vertical here. This is our center. If it's length 16, if the major axis is length 16 and the center is right in the middle of the major axis, then we have 8 units above and 8 units below to give that total of 16. So we have 8 units up here and 8 units down here. You see, so from this center point I can count up 1, 2, 3, 4, 5, 6, 7, 8, you see, to be one end of the major axis. The other end is down here. 1, 2, 3, 4, and then another 4 down here. There's the other end. What are the coordinates of these points? Well, we may or may not need the coordinates of the point. It's really the distance from the center to the ends that we're after. And this is 4, and that's another 4. Gee, that's 8. So we know then that the A value is 8. So this tells us that A is equal to 8. Now, if A is 8, we can come back here, and let's see, the A squared is in this denominator, so we have 8 squared here. Looks like we need the B value. Now we have A and C, so we can make the calculation for B. And we do that like this. So we come out to the side and we think, well, C squared is A squared minus B squared. And let's see, the C distance is 4. So 4 squared is, the A distance is 8. So we have 8 squared minus B squared. B squared then is equal to 8 squared 64, 4 squared 16. So B squared then is 64 minus 16, looks like about 48. B squared is 48. Do we really need B? No, we don't need B. We need B squared. That's what goes into this denominator. So this denominator is going to simply be 48. And we'll clean up a little bit. X minus 0 is simply x, so we have x squared then over 48 plus y minus 4 squared over 64 equals 1 as the equation associated with that information.
A most interesting characteristic of the ellipse is a reflective quality between the foci, as shown here. An emission from one focus will bounce off the wall of the ellipse and reflect upon the other focus. This characteristic is used in a process called lithotripsy, which is a hospital procedure that disintegrates gallstones and kidney stones. In the procedure, the patient is placed into a liquid medium and half of an ellipsoid is positioned so that the stone is at one focus. Using an electrical gap, a disturbance is created at the other focus. The disturbance emanates from the focus in all directions, bounces off the wall of the ellipsoid, and concentrates its impact on the stone at the other focus. Using repeated disturbances, the stone is disintegrated. Here's a portion of a film clip about lithotripsy.
In completely unbloody extracorporeal lithotripsy, the essential thing is exact positioning of the kidney stone in the body at the focal point of the shock wave ellipsoid. This is facilitated by a stretcher, which is hydraulically adjustable in extremely small steps and on which the patient is strapped so that the kidney area of the back lies exposed above the half-open ellipsoid. The shock wave is generated in the first focal point with the help of the shock wave electrode. 2 X-ray image amplifiers permit precise three-dimensional positioning of the stretcher so that the kidney stone is placed exactly at the point of maximum effect of the shock wave. As soon as the stone appears in the crosshairs of the X-ray monitors, the doctor can begin applying the shock waves. Generated in the ellipsoid underwater, the shock wave triggered by the electrode passes through the water in the bath into the patient's body, reaches the kidney stone, and disintegrates it to a fine-grained debris. The destruction of the stone structure is caused by the high-pressure amplitude in the second focus of the ellipsoid. In the course of a treatment, about 800 to 1,000 shock waves are reckoned with, which as a rule are automatically controlled in rhythm with the heartbeat. On the X-ray monitor, the disintegration of the stone is already clearly evident.